Hello students, it is the third class to discuss about the properties of D and A block elements. Now we have to discuss the catalytic properties of transition metals. Means the transition metal and their compounds are used as a catalyst. The catalytic properties of a transition metal is mainly due to their variable oxidation state, and they can form complex. When they are used as a catalyst on the surface of the metal, the reactant atom or molecules will adsorb on the surface of the solid, and that solid surface will make a bond with atoms of that reactant molecules, so that the bond among the reactant molecule become weak. The bond among the reactant molecule become weak, which can easily break, and this possesses low energy of activation. As this possesses low energy of activation, the reaction rate increases. As transition metal possess variable oxidation state, they are used as a effective catalyst. For example, iron 3 plus. Iron 3 plus can be used as a catalyst in the reaction between iodide with porous sulfate. To form I2 and sulfate. How? First, Fe3 plus, this can act as an oxidant, and I minus can act as a reductant, so that ferric form is converted to ferrous and iodide converted to iodine, and ferrous form also act as a reductant. This combined with the porous sulfate, the ferrous again convert to ferric and porous sulfate convert to sulfate form. So Fe3 plus, finally we get Fe3 plus. So Fe3 plus can be used as a catalyst due to its variable state. And during catalysis process, the ferric form is converted to ferrous, and the ferrous form again come back to ferric form. So the transition metal, due to their variable state, can be used as a catalyst. You may remember which catalyst is used for which process. For example, iron is used as a catalyst in the manufacture of ammonia by Haber's process. Vanadium pentoxide is used in the manufacture of H2SO4 in contact process. Platinum is used in the Ostwald process. Nickel is used in the hydrogenation of oils. So you may remember all the catalysts, and they are used in the various process. Then formation of alloy formation. As transition metal have nearly same atomic radius, So they can form a homogeneous mixture. They can combine together to form a homogeneous mixture, and that is called alloy. Due to alloy formation, they have high melting point and they are also extremely hard. So the various metal can combine together to form alloy. You may remember different types of alloy. For example, bronze. The bronze contains copper and tin in a appropriate proportion. The proportion you may remember. Your copper is 75% and tin is 25%. Brass. The brass also contains copper and zinc. Gunmetal, copper, zinc, tin. You remember all the alloy form and their composition. Then oxide formation. Except scandium. Except scandium, other metal of a transition metal form metal oxide MO, where the state of metal is +2. The state of metal is +2. But scandium oxide not exist in this form. The scandium form Sc2O3, where the state of a scandium is +3. The nature of a MO, is ionic. The nature of MO is ionic. And depending on their higher oxidation state, they can form higher oxides. Like Mn. The higher state of manganese is +7, so it can form Mn2O7. The maximum state of chromium is +3, it can form CrO3. So from scandium to manganese, in their higher state, they can form higher oxide. But beyond manganese, no higher oxide we can get above Fe2O3. Above Fe2O3, you will not get any other higher oxides, because in higher state they do not exist. Besides some oxide, they also form some oxocation. Like VO2 plus, VO2 plus, TiO2 plus. They form such oxocations. Again, the higher oxides are usually covalent in nature. Higher oxides are covalent and the lower oxides are usually ionic in nature. As higher oxides are covalent in nature, for example, Mn2O7, CrO3, vanadium pentoxide V2O5. As these oxides are covalent in nature, they usually possess low melting point. Again, higher oxides are usually acidic in nature. For example, Mn2O7 is acidic in nature. This can be converted to HMnO4. HMnO4. This nature is acidic. And CrO3 is converted to either chromic acid or dichromic acid, H2Cr2O7. So these two oxides are usually acidic in nature. But vanadium pentoxide, this nature is amphoteric. And this can be converted to cationiform VO2 plus and anioniform VO4 3 minus. Either cationiform VO2 plus or anioniform VO4 3 minus. And the lower oxides are usually basic nature. For example, MnO, CrO, this nature is basic. But Cr2O3, this nature is amphoteric. Then potassium dichromate K2Cr2O7. First, preparation of a potassium dichromate K2Cr2O7. How can prepare potassium dichromate? The potassium dichromate can prepare. The main source is chromite ore. The formula is FeCr2O7. FeCr2O4. On reaction of the sodium carbonate in the presence of air, it is first converted to sodium chromate Na2Cr4. Sodium chromate form. Actually, the sodium chromate in acidic medium. Actually, chromate form in acidic medium is converted to dichromate form because the dichromate form is more stable in acidic medium. So sodium chromate is converted to sodium dichromate Na2Cr2O7 and which dissolve in KCl to convert to K2Cr2O7. This is potassium dichromate. The main important point is that the chromate form in acidic medium is converted to dichromate form Cr2O7 2 minus form. But the dichromate form again come back to chromate in basic medium. This means the chromate is stable in basic medium and dichromate is stable in acidic medium. If we use H plus, the reaction proceed to dichromate form. If we use basic medium, the dichromate is converted to chromate. Acidic medium, chromate convert to dichromate. Basic medium, dichromate convert to chromate form. Look at here. In a basic medium, the chromate formula exists. In acidic medium, dichromate formula exists. If we use H plus, the chromate is converted to dichromate. If we use basic medium, the dichromate come back to chromate form. Okay. Then the structure of a chromate and dichromate. Actually, they have sp3 hybridization. The structure is tetrahedral. Chromium. The structure is tetrahedral. So this is the structure of a chromate. The structure of a chromate. Look at here. The structure of a chromate. Cr double bond O minus O minus. Resonance is possible among them. So all cases chromium oxygen possess same bond length. In chromate, the bond length of a CRO remains same because of a resonance. Then what is the structure of a dichromate? The structure of a dichromate is there. There is some CR-O-CR linkage, and every CR contains 3 pi bond O. 3 pi bond O. So these CR pi bond O and these CR pi bond O. There are 6 CR pi bond O. All possess 6 CR pi bond O. Among these, resonance is possible and they possess same bond length. But look at here about this. Among these CR-O-CR, resonance is not possible. And there are 8 CR-O oxygen bond, but 6 CR-O oxygen bond have same bond length and 2 CR-O bond has same bond length. 2 CR-O has same bond length. Because resonance is not possible among CR-O-CR, but resonance is possible among 6 CR-O bond length. Then properties of a potassium dichromate. Properties of a potassium dichromate. The potassium dichromate can act as strong oxidizing agent. So the dichromate in acidic medium gains 6 electrons to convert to chromium 3 plus. The convert to chromium 3 plus dichromate form in acidic medium is converted to chromium 3 plus. The color of a dichromate is usually orange. This convert to green color of a chromium 3 plus. And this possess a reduction potential of a plus 1.33 volt. Means this possesses positive reduction potential. As this possesses positive reduction potential, this can act as better oxidizing agent in comparison to H plus. And it can oxidize iodide to iodine, hydrogen sulfide to sulfur, stannous to stannic, ferrous to ferric, and itself undergoes reduction to convert to chromic form. You may write the equation. For example, you write one equation, dichromate. Dichromate combined with I minus in the presence of H plus. The dichromate form in acidic medium is converted to chromium 3 plus, and I minus is converted to I2 and H plus in the form of water. So oxidant dichromate is converted to chromium 3 plus. I minus reductant is converted to I2. Iodide to iodine, hydrogen sulfide to sulfur, stannous to stannic, and ferrous to ferric. Then potassium permanganate. First, preparation of potassium permanganate. The main source is MnO2, manganese dioxide. In basic medium that undergoes oxidation with air to form potassium manganate K2MnO4. Potassium manganate plus water. Actually, potassium manganate in acidic medium is unstable. This undergoes disproportionation reaction to convert to permanganate permanganate plus manganese dioxide plus water plus water plus water. Actually, you have to use acid, some acid, to convert manganate to permanganate. Actually, once in NEET exam, one question is there: which is the best acid? Which is the best to convert the reaction in a forward direction, means towards formation of a permanganate? The choice was carbon dioxide, sulfur dioxide, HCl and KOH. The first choice is carbon dioxide, second choice sulfur dioxide, third choice HCl and fourth choice was KOH. If you use KOH, the reaction will proceed backward direction, means the formation of a permanganate will be less. The formation of a permanganate will be less. But if we use sulfur dioxide, the nature is acidic. HCl, nature is acidic, but these two are a reducing agent. As these two are reducing agent, they further combine with the permanganate, which act as oxidizing agent. So they will consume permanganate and the reaction proceed forward direction, and the yield of permanganate will be less. But if we use carbon dioxide, which nature is only acidic nature, only acidic in nature, and this will proceed the reaction in a forward direction to give the more amount of permanganate. The yield of permanganate will be more in the presence of carbon dioxide. So answer is carbon dioxide, not sulfur dioxide, not HCl, because they will consume permanganate and the formation of or yield of permanganate will be less. Another method is there. First, MnO2 on fusion with the KOH and oxidized with the Ar or KNO3, potassium nitrate, it is converted to manganate. Means manganese dioxide on reaction with the fused KOH and oxidation with the Ar or potassium nitrate, you get potassium manganate or manganate form. The manganate on electrolytic oxidation means oxidation in electrolysis process in alkaline medium, this converted to manganate, permanganate. So manganate on electrolytic oxidation in alkaline medium, this converted to permanganate. The permanganate also prepared in the laboratory. If we use Mn2 plus manganese sulfate, manganese on reaction with the ferrous sulfate, H2O8 2 minus ferrous sulfate, the manganese form on reaction with the ferrous sulfate is converted to permanganate, and ferrous sulfate is converted to sulfate. This is the laboratory method of preparation of permanganate. The potassium permanganate undergoes decomposition. The potassium permanganate undergoes decomposition by the action of heat, convert to potassium manganate plus manganese dioxide plus oxygen. So oxygen can prepare by heating potassium permanganate. Then the structure of manganate and permanganate. Structure of manganate and permanganate. Actually, the color of manganate is green. The color is green. This is manganate. Mn double O O minus O minus. This is actually manganate. The color is green color. And this is the structure of a permanganate. The structure is tetrahedral. The color is purple color. The color is purple color. So this is structure is permanganate. Mn double and O, only O minus, only O minus, only O minus. The structure of a permanganate as the hybridization is sp3, the structure is tetrahedral. Then the properties of a potassium permanganate. The potassium permanganate can act as strong oxidizing agent. Strong oxidizing agent. In different medium, it is converted to different form. In different medium, it is converted to different form. For example, MnO4 minus in no acid medium or in basic medium is converted to manganate form. Means permanganate is converted to manganate. The medium is basic. Or permanganate in neutral medium or weak acid medium is converted to MnO2, or weak basic medium is converted to MnO2 form. And if the medium is strongly acidic, it is converted to Mn2 plus. So that in a basic medium you get MnO4 minus. In neutral medium or weak basic medium, convert to MnO2. In acid medium, converted to Mn2 plus. Means depending on the concentration of H plus ion, we get different form of manganese. Either you get manganate or get MnO2 or get Mn2 plus. That depends upon the medium. Look at here. In acid medium, it is converted to Mn2 plus. For example, I minus act as a reducing agent. MnO4 minus act as a oxidizing agent in acidic medium. The medium is acidic. Permanganate is converted to Mn2 plus. Iodide is converted to iodine and water for balance. Exactly same way, ferrous form is converted to ferric form, and permanganate is converted to Mn2 plus. The medium is acidic. Again, oxalate convert to carbon dioxide, permanganate convert to MnO2. Hydrogen sulfide convert to sulfide. Hydrogen sulfide convert to sulfur. Hydrogen sulfide is a reducing agent, convert to sulfur, and permanganate is convert to Mn2 plus. Again, sulfide form is convert to sulfate form. ITE form convert to AT form. IT convert to AT. ITE convert to AT. Sulfite to sulfate, nitrate to nitrate, ferrite to ferrate. But in neutral medium or fairly alkaline medium, the MnO4 minus is converted to MnO2 form. Look at here. If you will use iodide, permanganate plus iodine, if the medium is basic or slightly basic nature or alkaline nature, first you get MnO2, and iodine will give I2, and I2 combine with base to form iodate Ki3 minus. As medium is alkaline or slightly alkaline. Again, thiosulfate convert to sulfate form. Thiosulfate convert to sulfate form. If the medium is alkaline. And if MnO4 minus, also Mn2 plus act as a reducing agent, is converted to MnO2. So these are the properties of a potassium permanganate.